Good evening, students. So in last class, we have completed the third unit. So in today's class, we are going to start fourth unit. So the fourth unit is going to deal with silent pole missions, and the silent pole missions performance can be understood by using two reaction theory. Two reaction theory of salient pole missions. Okay. Now, just if we recall the EMF method of voltage regulation, EMF method of voltage regulation. So in this, we have introduced the concept of synchronous reactance. We have used the concept of synchronous reactance. The synchronous reactance is given by the sum of XL and XA. XL is leakage reactance and XA is armature reaction reactance. So here, the armature reaction effect, whatever the armature reaction effect, the armature reaction effect has been considered by using a single reactance XA, a single reactance XA. But this concept of using a single reactance to represent the armature reaction is applicable to cylindrical rotor missions only. Cylindrical rotor alternators only. Not only alternators, in case of motors also, the equivalent representation of armature reaction by using a single reactance value is applicable to only cylindrical rotor missions. Why? Because you see cylindrical rotor synchronous mission, suppose this is stator, then the rotor will have cylindrical shape, and this is cylindrical rotor mission. Now if you see silent pole rotor mission, suppose this is stator, the rotor will be like this. This is salient pole rotor mission. Now, if you observe in cylindrical rotor mission, the air gap is going to be almost same. If you consider the air gap at any point. So this air gap is going to be constant or it is going to be uniform. Air gap is uniform irrespective of the rotor position. So rotor ఈ పొజిషన్ లో ఉన్నా లేదా రొటేట్ అవుతూ certain angle rotate అయినా కూడా the air gap between the rotor and stator is almost constant. Therefore, the cylindrical rotor alternator is going to have uniform air gap. Whereas if you see here, in case of Salient pole machine, when the rotor is in this position, here we are going to have minimum air gap and here maximum air gap. Now, once the rotor starts rotation, if the rotor is going to rotate by certain angle, then the minimum air gap position and maximum air gap position is going to change. So stator ilane undi anukunnam. So stator is not going to rotate. Stator is stationary. So stator remains in this position. Now, let us assume that the rotor has been rotated by certain angle. The rotor has been rotated by certain angle. Now I am assuming 90 degrees. It has been rotated by 90 degrees. The rotor has been rotated by 90 degrees. Then along the here we are going to have minimum air gap and here we are going to have maximum air gap. So in case of Salient pole machines, with the change in rotor position, the air gap between the rotor and stator is going to change. Therefore, the reluctance offered by the air gap to the magnetic flux path is going to change. Whereas in case of cylindrical rotor machines, as the air gap is uniform, the reluctance offered by the air gap to the magnetic flux is going to be same. So here, non-uniform air gap. So in cylindrical rotor machines, as air gap is uniform, the reluctance offered by the air gap to the magnetic flux is constant. As the magnetic flux ని అపోజ్ చేసే రిలక్టెన్స్ కాన్స్టెంట్ ఉంది కాబట్టి సో we can take XA to represent the armature reaction effect. So in order to represent the drop due to armature reaction, can represent the drop by using a single value of XA. But in case of Salient pole machine, air gap is not uniform. the air gap is not uniform. Therefore, the reluctance offered by the air gap to the flux path is going to change, or it changes with rotor position. Therefore, we cannot implement the concept of synchronous reactance. So, synchronous reactance concept where we have used a constant XA to represent the armature reaction effect cannot be used for Salient pole machines. We can't implement the concept of synchronous reactance for Salient pole machines. Okay. So, whatever the concept that we have studied in third unit for determination of voltage regulation, the same methods we cannot implement for Salient pole machines. The reason is the reactance offered by the synchronous, the reluctance offered by the air gap to the flux path is going to change with rotor position. Any doubts in this? ఏమైనా డౌట్స్ ఉన్నాయా? రిలక్టెన్స్ అంటే ఏమి? వాట్ ఈస్ మీన్ బై రిలక్టెన్స్? రెసిస్టెన్స్ అంటే ఏమి? వాట్ ఈస్ మీన్ బై రెసిస్టెన్స్?
It opposes the current.
ఏ సర్క్యూట్ లో? ఎలక్ట్రికల్ సర్క్యూటా, మ్యాగ్నెటిక్ సర్క్యూటా, మెకానికల్ సర్క్యూటా?
Electrical circuit, sir.
ఎలక్ట్రికల్
Reluctance
సర్క్యూట్.
అంటే opposing of magnetic flux.
సో ఎలక్ట్రికల్ సర్క్యూట్ లో కరెంట్ ఫ్లో అవుతుంది. కరెంట్ కి అపోజిషన్ ఏదైతే క్రియేట్ అవుతుందో ఆ ప్రాపర్టీని electrical element property which opposes the flow of current is called as resistance. Similarly, in the magnetic circuit, the property of the element which opposes the flow of magnetic flux is called as reluctance. So, reluctance అనేది ఎయిర్ గ్యాప్ లో మనం ఫ్లో కావాలి కాబట్టి ఫ్లక్స్, సో ఆ ఫ్లక్స్ ఫ్లోని అపోజ్ చేసిన రిలక్టెన్స్ అనేది సిలిండ్రికల్ రోటార్ మిషన్ లో అయితే ఎయిర్ గ్యాప్ యూనిఫామ్ గా ఉంది కాబట్టి రోటార్ ఏ పొజిషన్ లో ఉన్నా ఆ ఎయిర్ గ్యాస్ క్రియేట్ చేసే రిలక్టెన్స్ అనేది కాన్స్టెంట్ గా ఉంటుంది. సో ద ఆర్మేచర్ రియాక్షన్ ఎఫెక్ట్ వీ కెన్ రిప్రజెంట్ బై యూజింగ్ ఎ సింగిల్ రియాక్టెన్స్ వాల్యూ. Whereas in case of silent pole missions, as the air gap is dependent upon the rotor position, sometimes it is minimum, sometimes it is maximum. So as the air gap is changing, the reluctance offered by that air gap to the magnetic flux path is also going to change. The reluctance is not going to be constant. It's going to depend upon the rotor angular position. Therefore, we cannot represent the armature reaction effect by using a single reactance. Hence, the concept of synchronous reactance we cannot implement for silent pole machines. So, this problem of having variable reactance has been solved by using Blander's two reaction theory. So, the problem of variable reluctance in Salient pole missions can be overcome by using Blandel's two-reaction theory. So by using the concept of two-reaction theory, we can resolve the problem of multiple or variable reluctance by Blondel. So Blondel is the scientist name who proposed this two-reaction theory. Let us see what is Blondel's two-reaction theory. First, let us consider a Salient pole synchronous mission. About this is stator. Let us consider A phase windings here. This is A dash. Next, with an 120 degrees displacement, B dash. Next, with 120 degrees displacement from B, we will have C dash. Now, let us consider the rotor along phase A. That means the rotor south pole and north pole are facing the armature terminals A dash and A. So this is north pole, this is south pole. Now let this is field winding. Current in inward, outward direction. The upper conductors are having current in inward direction and downward conductors field currents in upward direction. Now let us assume the rotor is moving in anti-clockwise direction. The rotor is moving in anti-clockwise direction. Then we will have the induced EMFs in the conductors or coil sides and the north pole in outward direction. The EMFs in the conductors and the north pole will have outward direction, and the conductors or coil sides and the south pole influence will have induced EMF in inward direction. Therefore, A, B dash, C dash will have outward EMF, and the coil sides B, A dash, C dash will have inward. So outward direction is represented by dot, inward direction is represented by cross. Now, as the north pole and south pole are facing coil sides A dash, the coil A will have maximum induced EMF. So this is the position when the coil A is having maximum induced EMF. Now, if you draw an axis along with the north pole and south pole of the rotor, this axis is called as field axis. is called as field axis. So here we are having maximum EMF position. Now, this field axis is also called as D axis. D axis is nothing but direct axis. This is a short form of direct axis. Now, we can also draw phase A axis. Phase A axis means it is the axis which is perpendicular to the line joining A dash. So A dash ఈ టూ కాయిల్ సైడ్స్ ని జాయిన్ చేసే లైన్ కి పర్పెండిక్యులర్ గా ఉండేది ఫేజ్ A యాక్సిస్. నెక్స్ట్ సిమిలర్లీ ఫేజ్ B యాక్సిస్ విల్ బి పర్పెండిక్యులర్ టు ద లైన్ జాయినింగ్ ఆఫ్ B డాష్. సో B డాష్ పర్పెండిక్యులర్ గా జాయిన్ చేసి ఒక లైన్ డ్రా చేసి దాని పర్పెండిక్యులర్ ఉండేది ఫేజ్ B యాక్సిస్. సిమిలర్లీ C డాష్ కి లైన్ జాయినింగ్ C డాష్ కి పర్పెండిక్యులర్ ఒక లైన్ డ్రా చేస్తే అది ఫేజ్ C యాక్సిస్ అవుతుంది. So here we are going to consider only phase A axis. So if I consider phase A axis, then the phase A axis, so phase A axis, so line joining A dash perpendicular ga the axis perpendicular to line joining A dash is called as phase A axis. So this axis is now perpendicular to A dash. So it is also called as phase A axis. Now, if you consider this axis, it is at an angle 90 degrees to the D axis. So we can also call this axis as Q axis. Q axis. So Q axis is axis which is perpendicular to D axis. So here we have considered three axes. One is field axis or D axis. The D axis is along the field poles. So N కు S కి. So field poles కి along గా మనం డ్రా చేసిన యాక్సిస్ వచ్చి ఫీల్డ్ యాక్సిస్ ఆర్ D axis అంటాము. నెక్స్ట్ దానికి పర్పెండిక్యులర్ గా డ్రా చేసిన యాక్సిస్ Q axis. In addition to the D axis and Q axis, we can have phase A axis. That phase A axis is going to be perpendicular to line joining of A dash. So A dash join చేసి ఒక లైన్ డ్రా చేస్తే A dash ఇక్కడ A ఉంది, ఇక్కడ A dash ఉంది. సో రెండింటిని జాయిన్ చేసి ఒక లైన్ డ్రా చేసి దానికి పర్పెండిక్యులర్ గా ఒక యాక్సిస్ డ్రా చేస్తే అది phase A axis అవుతుంది. Phase A axis. So in our present position of the rotor, so rotor ఈ పొజిషన్ లో ఉన్నప్పుడు phase A axis, Q axis both are coinciding with each other. Phase A axis, Q axis రెండు ఒకదానికి ఒకటి coincide అవుతున్నాయి. Now this is the maximum EMF position. Now let us consider a position such that, suppose let us consider the internal power factor internal power factor angle as psi. So I am assuming that the internal power factor angle as psi degrees. What is by power factor angle? Power factor angle అంటే ఏమి? What is by power factor angle?
The cosine angle between voltage and current, sir.
అది power factor. So the angle between voltage and current.
Current.
Voltage and current మధ్య angle power factor angle. So theta is power factor angle. Power factor angle. So if you take the angle between V and I, so V is terminal voltage. So it gives mission power factor or load power factor. Mission power factor or load power factor. Cos theta gives load power factor. Okay. Now we are considering here internal power factor. Internal power factor angle. So here the same relation between the voltage and currents that we are going to take, but here the armature current IA is going to be considered with the displacement with respect to the induced EMF EF or E naught. Induced EMF EF or E naught. So this angle we are taking as psi. So the angle between the induced EMF EF is induced EMF. Induced EMF, that is E naught that we have considered in case of cylindrical machines. So cylindrical rotor machines lo manam E naught anukunnam kada, no load induced EMF. So induced EMF E naught ni mana silent pole machines lo EF anukuntunnam ante teda. So EF is the induced EMF. The induced EMF ki armature current ki madhyalo unde angle psi. Therefore internal power factor will become cos psi. And ఇప్పుడు మన ఈ phi power factor angle అంటే దాని ఎక్స్ప్లెనేషన్ ఏమి? The current is going to become maximum after an angle of psi degrees from the voltage maximum position. So theta degrees lagging లో ఉందంటే అర్థం ఏమి? వోల్టేజ్ మాక్సిమం అయిన theta angle తర్వాత I maximum reach అవుతుంది. Suppose this is the voltage vector, then I is lagging theta means I is going to start theta degrees lately. That means I will become maximum. The maximum value of I will be attained after theta degrees from the maximum position of V. So V ki theta degrees lagging లో ఉంటుంది. సో ఇప్పుడు మనం కన్సిడర్ చేసుకున్న ఇన్స్టెంట్ ఇక్కడ రోటర్ ఈ పొజిషన్ లో ఉన్నప్పుడు ఏలో మ్యాక్సిమం ఈఎంఎఫ్ ఉంది. ఇప్పుడు నాకు మ్యాక్సిమం కరెంట్ పొజిషన్ కావాలి అంటే ఈ రోటర్ అనేది psi degrees రొటేట్ కావాలి. సో ఇక్కడ psi degrees were taken as internal power factor angle. Therefore if the rotor rotates by an angle psi degrees, then the coil sides A and A dash will have maximum current position. So this is the position that we have considered up to now. So at this point, the coil sides A and A dash are having maximum EMF. Now, in order to get the maximum current, the rotor has to be rotated by an angle psi degrees from this position. సో ఈ పొజిషన్ నుంచి రోటార్, సో ఇంతకుముందు ఈ పొజిషన్ దగ్గర ఉంది, ఈ పొజిషన్ నుంచి ఇఫ్ ద రోటార్ రొటేట్స్ బై అన్ యాంగిల్ 60 degrees, rotor is horizontal in the initial conditions when the A dash is having maximum EMF. Now, if the rotor rotates by an angle 60 degrees, as the internal power factor is psi, now the coil sides A dash will have maximum current. So maximum armature current position is this one. Now, when we are having maximum armature current, so this is stator, this is D axis initially. Now the rotor has been moved by an angle 60 degrees. సో ఈ పొజిషన్ నుంచి హారిజాంటల్ పొజిషన్ నుంచి రోటార్ 60 degrees రొటేట్ అయింది. ఇది నార్త్ పోల్, ఇది సౌత్ పోల్. దేర్ ఫోర్ the D axis will be now this one. This is D axis that they have represented here. So field axis and D axis. Now perpendicular to this we are going to have Q axis. This is Q axis, but the conductors, that is A and A dash, are not moved. They are on stator, so they have still remains there itself. Therefore, the phase A axis will be always perpendicular to A dash, phase A axis. So this is phase A axis. So A dash position change kala kabatti phase A axis positions change kaadu. So phase A axis is always perpendicular to line joining of A dash. So A dash perpendicular ga phase A axis undi. So rotor position change ayindi kabatti D axis position, Q axis position change ayinayi. Now the coil sides A and A dash are having maximum current. Therefore, the armature flux and the armature MMF will act along the phase A axis. So the armature MMF, whatever the MMF created by armature flux, will act along the phase A axis. So A dash lo maximum current undi kabatti A dash is carrying maximum current, carrying maximum armature current, maximum armature current. Therefore, the FA acts along phase A axis. Phase A axis. Okay. Now, if you see, the air gap along the phase A axis is going to change with the rotor position. So as the rotor is changing its rotation, as the rotor is rotating, the position of the rotor is changed. As the position of the rotor is changed, the air gap offered along the phase A axis is going to change. Therefore, the reluctance offered to the FA by the air gap is going to change. Hence, the reluctance will depends upon the psi value. So this is field axis. So along this field axis, we are going to have FF. Now, the FF and FA are displaced by an angle 90 plus psi. So FA నుంచి Q axis మధ్య angle psi కాబట్టి ఈ angle psi. So psi angle rotate అయింది. Now Q axis కి D axis మధ్యలో 90. Therefore, the FA and FF are displaced by 90 plus psi angle. As the psi is going to change, the effect of armature reaction, that means the effect of FA and FF is going to change. Therefore, the armature reaction effect is not constant. So to overcome this problem, what the Blondels has suggested is he has resolved this FA into two components. So FA ni two components resolve chesadu. So this is one component. This is one component, horizontal component, vertical component. So the FA is resolved into two components. This is one. This is one. So one component along D axis, one component along Q axis. So the FA is resolved into two components, one along the D axis, one along the Q axis. This D axis component is denoted by FD, Q axis component is denoted by FQ. So that FA is resolved into two components, FD and FQ, one along the direct axis, one along the quadrature axis. Now, if you observe, what are the rotor position? That FD is always along the D axis. So what about the air gap along the D axis? But it's going to change, that remains constant. Rotor ఏ పొజిషన్ లో రొటేట్ అవుతూ ఉన్నా నార్త్ పోల్ సౌత్ పోల్ డైరెక్షన్ లో రోటార్ కి స్టేటర్ కి మధ్య ఎయిర్ గ్యాప్ కాన్స్టెంట్ గా ఉంటుందా, చేంజ్ అవుతూ వెళ్తుందా?
కాన్స్టెంట్ గానే ఉంటుంది సార్.
కాన్స్టెంట్ గా ఉంటుంది. ఈ క్యూ యాక్సిస్ అంటే మిడ్ పాయింట్ ఆఫ్ పోల్. సో ఈ పాయింట్ దగ్గర తీసుకుంటే ఎయిర్ గ్యాప్ చేంజ్ అవుతూ ఉంటుందా, కాన్స్టెంట్ ఉంటుందా?
కాన్స్టెంట్ గానే ఉంటుంది సార్.
సో వాట్ ఎవర్ మే బి ద రోటార్ పొజిషన్, the FD will have a minimum constant reluctance. So the air gap is minimum, so the reluctance is minimum, and FQ will have a maximum but constant reactance. Air gap is maximum, so constant reluctance. So the reluctance is not going to change. So by resolving that FA into two reactances FD and FQ, we can make the armature reaction effect to be constant along the direct axis and along quadrature axis. So what is the responsible component for the production of FA? The FA, the armature reaction MMF is produced due to armature flux. It is due to by the armature flux, it has been produced. So phi A is due to armature current. So IA is responsible component for the production of FA. Similarly, the FD and FQ are also produced by the armature current components along the direct axis and quadrature axis. So this IA is also resolved into two components along the direct axis and along the quadrature axis. So FD is produced by corresponding armature current ID. FQ is produced by corresponding armature current IQ. So we are having different components on the direct axis and different components along the quadrature axis. So which components are called as direct axis components? Which components are called as quadrature axis components? So the components which are in phase with direct axis are called as direct axis component, and the component which is along the Q axis is called as Q axis component. Now if you see here, what is the value of ID and IQ? So this is okay. After phasor diagram, we will get the ID and IQ. Let's forget about it. Okay. Now let us see the phi d is produced by id and phi q is produced due to iq, and this id and iq will produce a flux, armature reaction flux phi ad and phi aq. Let us take this phi d and phi q as phi ad, phi aq, armature reaction. So phi d is resolved into phi ad, phi aq. Phi aq, phi ad. So armature flux along d axis, armature flux along q axis, armature MMF along direct axis, armature MMF along q axis, FAD, FAQ. Now, you find the ratio of phi AD by phi AQ. It is never equal to phi AD by phi AQ. The reactance or the reluctance offered along the direct axis and quadrature axis is not going to be same. The reluctance, that means the air gap reluctance along the direct axis and quadrature axis is not going to be same. Therefore, the corresponding flux and MMF ratio is not going to be same. So the flux vector and MMF vectors are going to be displaced by certain angle. Now, if you consider this phi AD is produced due to this ID. Therefore, this phi AD drop can be represented by using minus J ID into XAD by using a reactance XAD, similar to synchronous missions, cylindrical rotor synchronous mission where we have used XA. Here we are using a 50 degrees reactance XAD to represent the armature reaction drop due to FAD along the direct axis. Therefore, this EAD, armature reaction drop along the D axis, can be represented using JID into XAD. This ID XAD is represented using minus. So this minus indicates voltage drop. EAQ, similarly EAQ equal to minus JIQ into XAQ. Now, if you add this EAD and EAQ to the induced EMF, EF plus EAD plus EAQ, we will get AR, air gap induced EMF, ER. So to the EF, if we add EAD and EAQ, then we will get air gap induced EMF. So this will come across in cylindrical rotor missions. So what is the ER formula that we have derived there? మనకు అక్కడ వచ్చిన ER formula ఏమి? cylindrical rotor missions లో ER formula ఏమి వచ్చింది మనకు? ER V plus IARA plus JIXL అదేనా వచ్చింది. సో దానికి IXA డ్రాప్ యాడ్ చేస్తే మనకు E0 వస్తానండి. సో ER ఈక్వల్ టు ఆర్ E0 ఈక్వల్ టు ER ప్లస్ JIAXA మనం అక్కడ వచ్చింది. సో ER ఈక్వల్ టు E0 మైనస్ JIAXS. సో EAD EAకి ఇక్కడ మైనస్ రిప్రజెంట్ చేసినాం కాబట్టి ER ఈక్వల్ టు EF మైనస్ JIA minus JID XAD minus JIQ XAQ. So same formula we got here. ER equal to E0 minus JIA XA. So అదే ఫార్ములా ఇక్కడ మనం ER రిప్రజెంట్ చేస్తున్నాము. ఓకే, నౌ if you want to get terminal voltage, then from this ER we have to subtract the armature current, armature resistance drop and leakage reactance drop. So if we draw the phasor diagram, this is d-axis. So to this d-axis, so along this d-axis, we are going to have flux. Now, perpendicular to this, we are going to have EF. So to this, from this EF, if you subtract EAD and EAQ, that means minus J EAD minus JID XAD and EAQ minus JIQ XAQ, we are going to get ER. Now, if you take the voltage vector, the terminal voltage V will be will lag the EF by an angle delta. So terminal voltage V की induced EMF के मध्य angle delta अंटामो. Delta is called as power angle. It is angle between EF and V. EF की V की मध्य unde angle, load angle or power angle. Now, if you subtract armature resistance drop and leakage reactance drop from the CR, we will get the V. So, if you take armature current, IA, if theta is power factor angle, then it is the angle between V and IA. So, parallel to IA, we will have armature resistance drop. Perpendicular to that, we are going to have leakage reactance drop. So, this one will become IXL drop and this one will become IRA drop. IARA drop and this is IAXL drop. So, if you take this is O, this is A, this is B, this is C, this is D, this is E. Now, the CD represents minus J IA XL drop. Now, to this, if you add, so XAL, let us take. Now, this IA can be written as ID plus IQ into XAL. So, minus J ID XAL minus J IQ XAL. So, the leakage reactance drop is also resolved into two components, one along the direct axis, one along the quadrilateral axis. So, XD-IL drop will be perpendicular to XAL. Sorry, ID-XAL will be perpendicular to ID. So, if you resolve this IA into two components, IA into two components resolve just say. So, this one is ID along direct axis. This one is IQ. So, ID की perpendicular गा ID XAL ఉంటుంది. IQ की perpendicular గా IQ XAL ఉంటుంది. So, if you take this point as F, then it will be equal to this is DF and this is CF. IDXAL is DF and IQXAL is CF in this figure. Now, CD, we can write it as DF plus CF. So, now the terminal voltage V can be written as V equal to, so if we take this terminal voltage as VT, so VT equal to EF plus EAD plus EAQ EAQ plus so it is minus JID. So minus JID XAL minus JIQ XAL minus IARA. So EF ki EAD, EAQ, CF, DF and DE యాడ్ చేస్తే మనకు VT వస్తుంది. So this is EF plus EAD is minus JID XAD minus JID XAD minus JIQ XAQ minus JID XAL minus JIQ XAL minus IARA. So in this we're having ID term. So if you take JID as common, we'll have XAD and here we're having plus XAL. I have taken minus ID as common. Next, if I take minus JIQ as common, so this term XAQ plus XAL minus IARA. Now I can write this equation as minus JID XD minus JIQ XQ minus IARA. This is VT. So here XD equal to XAD plus XAL. Similarly, XQ equal to XAQ plus XAL. So this XD is called as direct axis synchronous reactance. And XQ is called as quadrature axis synchronous reactance. Now if you observe the formula for XD and XQ, the XD is given by XAD plus XAL and XQ is XAQ plus XAL. So in both cases, the leakage reactants we have considered to be same. That means the leakage reactants along the quadrature axis and direct axis are considered to be constant. But whereas the armature reaction reactances, as the air gap is changing, the armature reaction reactances XA is going to be different along the direct axis and quadrature axis. So XAD is the armature reaction reactance along the direct axis. XAQ is the quadrature axis reactance along the Q axis. Okay. Now by using this formula, we can redraw the phasor diagram. So I can choose phasor diagram ni redraw chesukovachu. So we can simplify it. So the phasor diagram will be like this. So this is D axis. Now we are going to have EF perpendicular to direct axis. Now the voltage vector V will be at an angle theta lagging with EF. So delta is load angle or power angle. Delta is called as load angle or power angle. It is the angle between V and EF. And IA, the armature current. IA will be at an angle theta lagging with V. Okay. This VT terminal voltage. So So in order to get the Vt, we have to subtract EAD drop and then EAD EAQ and then IA or a drop. Not EAD, it is ID, IQ కదా IQ, XAQ, this is ID, XAD, and the difference IA or A. That gives the terminal voltage Vt. Okay. Now, what is the angle between EF and IA? EF के IA के मध्य angle. EF के IA के मध्य angle. EF की IA के मध्य angle. What is the angle between EF and IA?
Delta plus theta, sir.
దాని ఇంకో పేరు చెప్పుకున్నాం మనము. EF is going to, so IA is going to lag the EF by how much angle? That we have considered here. ఎంత? Psi. Psi is the angle between EF and IA. Therefore, psi equal to theta plus delta. So this is for this case. Depending upon machine is going to change. So synchronous motor, generator, lagging power factor కనపడుతుంది, leading power factor కనపడుతుంది అని చెప్పేసి ఈ రిలేషన్ చేంజ్ అవుతుంది. For this case, so in this graph, we are getting psi equal to theta plus delta. So here we have considered Vt is lagging the EF. So Vt lags EF. So it is generator or motor. ET lags EF and generator motor. It is generator and IA lags Vt. So lagging power factor. So generator lagging power factor operator అయ్యేటప్పుడు psi equal to theta plus delta. Psi equal to theta plus delta, remember. So this is the phasor diagram as per two reaction theory. Okay. So next class we will see analysis of this phasor diagram.